In this clip, you can see our sensor unit in action. It consists of an ESP32 microcontroller with our custom-made PCB mounted directly on top. A blue LED on the board shows whether the boost converter is active. That's necessary to raise the ESP32's 3.6 volts to the 5 volts required by the sensor. Additionally, we've added 3 LEDs to visualize humidity levels. Red indicates very high humidity, like in a tropical rainforest. Yellow means it's a bit too humid and should be monitored. And green signals that the humidity is within a healthy range. The sensor also measures temperature and particulate matter, but for this project, we're focusing mainly on humidity. All sensor data is sent wirelessly to our central hub via Bluetooth Low Energy, or BLE. That hub then controls our dehumidifier, which we also designed and built ourselves. The dehumidifier uses a Peltier element, a small thermoelectric device. When powered, one side of the Peltier gets cold while the other side becomes hot. A CPU fan blows humid air over the cold side, causing moisture in the air to condense, just like it would on a cold glass. The warm side is cooled using a heat sink and an additional fan to keep the system stable and efficient. Everything is housed in a compact, 3D printed case optimized for airflow and easy assembly. An ESP32 inside the dehumidifier receives BLE signals from the hub and activates the unit only when needed. Together, this setup creates a smart and energy-efficient system to monitor humidity levels and reduce the risk of mold indoors. Now, let's walk through our full design process, starting with the dehumidifier, the core of our system. We began by creating a detailed CAD model to house the main components. After several design iterations, we 3D printed the parts, assembled the unit, and ran our first tests. One key measurement we focused on was the RPM of the fan, which allowed us to evaluate how efficiently it was circulating air, a crucial aspect for effective dehumidification. With the mechanical system in place, we turned our attention to connectivity. Using an ESP32, we explored Bluetooth Low Energy compatibility and were able to successfully pair the dehumidifier with a smartphone. This meant we could remotely control it, switch it on or off, and begin basic automation, all from our phones. The next step was designing the electronics. We built a custom PCB and KICAD. Its primary function is to boost the ESP32's 3.6 volt output up to a clean 5 volts, which is required by our air quality sensor. The board also incorporates connections for additional components we described earlier, including power inputs and data lines for sensor communication. After soldering and assembling the board, we were able to read real-time environmental data, such as humidity, temperature, and air quality, and send that data via BLE to a mobile device. This confirmed the electronics and communication systems were working as intended. Next, we turned our focus to the sensor module. We assembled the sensor itself, designed a protective case in CAD, and 3D printed a compact enclosure to house it, ensuring both durability and proper airflow for accurate readings. Finally, we integrated all components and tested the full system together. We published the live sensor data to a webpage where we could view graphs tracking changes over time. But more than just digital confirmation, we could physically verify the system's success by checking the dehumidifier's water basin and seeing how much moisture had actually been removed from the air.